We're going to continue on to our next example for finding the area of a region between two curves. This is our second of two examples. And the problem is to find the area of the region common to the two regions bounded by the following curves. So we have r equals -6 cosine theta, which is the circle, the darker circle here, and r equals 2 minus 2 cosine theta, which is the cardioid. So there's the cardioid. And it's going to be an important line there. And then this is the circle. So find the area of the region common to the two regions bounded by the following curves. So let's just find this top half and not worry about this bottom half. I'm not sure exactly what the book is asking for, but clearly if we found this top half, then we could just double it to find the bottom half. But this video is going to describe just finding the top half of the area there. So the area that we're finding is this. And what makes this problem tricky is that there is kind of two different regions here. One of them is this little bit up here that I'll shade in pink. And the other is this bit over here that I'll shade in this teal blue color. We have to find those as two separate regions, and then you got to be able to figure out which function is the boundary line for it. So if I'm just talking about this first bit, let's call that one A1. I'm going to find the area of A1. The radii that come from the origin and hit that are only hitting the circle function, the -6 cosine theta. So I have to know where that starts and where that stops. And so that looks to be that circle region is 0 when the angle is pi/2. And then it's stopping, the boundary of the circular region is stopping at 2 pi/3. So this integral will start at pi/2 and will stop at 2 pi/3. If this point of intersection wasn't given, then you would have had to set these two equations equal to each other and solve for that point of intersection. But since it's on here, I'm not going to stop and do that right now. So you should confirm that if you had an angle of pi/2 and you substituted it into the cosine function, that you would in fact get 0, to confirm that this point is 0 when the angle is pi/2. And so then this circle is the -6 cosine theta squared for the formula d theta. And we need a 1/2. Whew, almost forgot that. So that's the pink area there. And then this area, a sub 2, is given by 1/2 the integral that's starting at 2 pi/3 and ending wherever this angle is, which looks to be pi. You could double check to make sure if you plug in pi that you do in fact get 1, 2, 3, 4, which I will, because cosine of pi is -1, and so 2 minus 2 times -1 would give me 4. So I can be confident that pi is the right value there. And then in here I put 2 minus 2 cosine theta squared d theta. And then to get my total area, it will just equal A1 plus A2. And you could find the value of these integrals by hand and using the trig identities that we had, but I don't think that that's the best use of our time. This is example 3 in the textbook, and you could see the work all done out for it. I have already typed in the -6 cosine into y2 and 2 minus 2 cosine into y3, and then I set up this integral that is from pi over 2 to 2 pi over 3 of the function that I have in y2 squared, and 0.5, there's also a 0.5 in front of this, can't see the whole thing here. And then 0.5 for the second integral, 2 pi over 3 to pi of the function that I have typed in y3, which is this one. And then if you press enter on that, you get that the total area is 7.854. And I think that that's good enough for our purposes. Finding these actual integrals gets pretty tedious. You can try it on a few of the easier ones on your homework, and then one that's this complicated, you might need to just use the calculator. You don't have to if you want to try it. It's good practice, but it gets a bit tedious. I know that the hardest part is deciding kind of how to split up this integral. And now that you've seen this, I want to recap that one more time. So as I'm looking at this region here, I can tell that as the theta values are rotating through here, when they're in this region between pi over 2 and 2 pi over 3, I'm only hitting the circle, the function that I have traced in orange here. I'm not hitting the boundary of the cardioid at all. And then as soon as I get past 2 pi over 3 and I'm sending out radii from the origin, I'm only hitting the cardioid and I'm not hitting the circle at all. So that's how I know that my integral from pi over 2 to 2 pi over 3 is just involving the circle. And from 2 pi over 3 to pi, I'm just using the cardioid. And then I'm just taking those two areas and adding them together to get the total area. So thanks for watching. Good luck on the homework.